Hello everyone, I'm going to do some proper maths today. I'm going to talk about this equation, x to the n plus y to the n equals z to the n. I want to find solutions where x, y and z are integers. So let's take some examples. Let's do n equals 1. Then that's quite easy really. I've got 2 plus 3 equals 5 would be an integer solution. I hope I haven't blown your minds with maths too early. If we took n equals 2, we could have 3 squared plus 4 squared equals 5 squared, which is called a Pythagorean triple. For n equals 3, there are no integer solutions, and that's the same for n equals 4 or 5 or 6, and that's because this is Fermat's last theorem, which was proven by Andrew Wiles, which says that there are no integer solutions when n is a positive integer greater than 2. But the thing about Fermat's last theorem is it says nothing about when the exponent is not a positive integer. What about if it was a negative number or a rational number or an irrational number? Can we find integer solutions then? Well, we can. Here's an example. 32 to the power 1/5 plus 243 to the power 1/5 equals 3125 to the power 1/5. Or here's another example. 27 to the power 2/3 plus 64 to the power 2/3 equals 125 to the power 2/3. But some of you may have already noticed that these are actually cheats. All I've done here is taken the two examples I've already shown you and hidden them in a slightly clever way. And it turns out that when the exponent is rational, these kind of cheats are all the integer solutions that we can find. There are no other solutions. There is a truly marvellous proof of this, which this video is too short to contain, so let me give you the gist. What we're trying to solve is this equation. So we're having the exponent be a rational number, which I've written as k over m here. Or to put it another way, we are taking the nth roots of x to the power k, y to the power k, and z to the power k. So we're looking for these nth roots. Now they are also algebraic numbers, so when you're taking real roots, we can use properties of algebraic numbers to prove that these nth roots are integers. And if they're integers, then x to the k, y to the k, z to the k, well, they have to be powers of k, obviously, and they're going to have to be powers of m as well. So this equation actually turns into this, and after taking the nth root, we get a to the power k plus b to the power k equals c to the power k. A, B and C are integers here, which is Fermat's last theorem, which only has integer solutions when k is equal to 1 or 2. So we have solutions, but we're restricted by Fermat's last theorem, which seems perfectly reasonable to me. One word of warning though, because there is a sense where this is true. 1 to the power 5/6 plus 1 to the power 5/6 equals 1 to the power 5/6. But that seems like bunk, because clearly the left-hand side is equal to 2 and the right-hand side is equal to 1. Except it doesn't have to be. For example, a 5/6 root of 1 could be e to the pi I over 3. And another 5/6 root of 1 could be e to the 5 pi I over 3. And a third 5/6 root of 1 could be 1 itself. And then this becomes a true equation. And in this case, the nth roots are now complex roots. So if we allow complex roots, we can get some strange integer solutions. But we can prove that only happens when x equals y equals z, and m is divisible by 6, which I think is a bit of a surprise. Now the proof of that result uses Galois Theory, and if you're interested in the full proofs of these results, well, I will put a link in the description. Incidentally, whenever we have an integer solution with a positive exponent n, we automatically have an integer solution with a negative n. So if we take x to the n plus y to the n equals z to the n, and we divide through by x times y times z to the power n, we will get an integer solution with a negative exponent. So if I took an example like 3 squared plus 4 squared equals 5 squared, that will correspond with 20 to the power minus 2 plus 15 to the power minus 2 equals 12 to the power minus 2. And this works in both directions. Well, that was for rational exponents. What about irrational exponents? Well, first of all, do we even have integer solutions with an irrational exponent? Well, yes, we do, and that's actually quite easy to show. For example, we could look at this. 4 squared plus 5 squared is greater than 6 squared, but 4 cubed plus 5 cubed is less than 6 cubed. So there must be a value for the exponent n somewhere between 2 and 3, where 4 to the n plus 5 to the n equals 6 to the n. Now we know that can't be rational, it must be irrational, and in fact if you go searching for it, you'll find that n is equal to 2.4879 something something. So integer solutions with irrational exponents exist, but it would be nice to give you an example where we don't have to go searching for the exponent. So how about this? Let's look at this equation, x to the n plus x to the n equals z to the n. Well, if we divide through now by x to the n, we would have 2 equals z over x to the power n, and then n is the logarithm to the base z over x of 2. So if we take an actual example of this, let's take 4 to the n plus 4 to the n equals 5 to the n, then we can solve this for n. N would be the logarithm to the base 5 quarters of 2, which is equal to 3.106 and some stuff. And now let me do just one last example of an integer solution to Fermat's last theorem with an irrational exponent. And this one I like because I think it's quite clever. It uses the golden ratio. The golden ratio, which we write as phi, is equal to 1 plus root 5 over 2. Well, the golden ratio is the solution to this equation. 1 plus phi equals phi squared. Now let phi equal 2 to the power n. Then if we do that, 1 becomes 1 to the power n, phi becomes 2 to the n, and phi squared becomes 4 to the power n. So we've got a Fermat's last theorem type equation here, and you can solve this for n. The exponent will be the logarithm base 2 of the golden ratio, 1 plus root 5 over 2, and that is equal to 0.6942 and some stuff. Now there are no general results for Fermat's last theorem with irrational exponents, except we know that there are infinitely many integer solutions out there, so you might like to try to find one for yourself, and if you have been, thanks for watching.